and thank you particularly to everyone for coming, and thank you very much to the organisers for inviting me, and much more importantly putting on the workshop to begin with. It's been really interesting so far, and it's a really good thing to be talking about. So I hope we're going to carry on sharing lots of ideas and suggestions this afternoon, and so yeah, thank you very much. So the talk is on semantic spaces, successes and goals. I'll start with a couple of introductions, though. Like I say, or like Martha said, I'm Dominic. My background is particularly in geometry years ago, so a lot of the NLP I've worked on has been very much from this is a fun thing for a geometer to do, and a lot of the work I do now is very, very geometric. I'll talk about that in a second. And I'd like to sort of list this talk as really joint work with Trevor Cohen, who is a colleague and long-standing colleague and collaborator of mine at the University of Texas Health Sciences Institute in Houston. So let me explain and frame that a little bit. These questions have come up a bit already, and I have a couple of points in the talk where I'm going to do what would have been digressions, but they're kind of arising from conversations we've been having, so consider it sort of extemporization that I just wrote, obviously wrote a not very detailed slide for. So lots of people have asked what's Grab Technologies, what's Grab? It's started off as a taxi ride-hailing company in Malaysia. So if you're familiar with like big global names like Lyft, Uber, Didi in China, Grab does many of the same things in Southeast Asia. So imagine the following problem. You have a pickup point and a drop-off point and a map of Singapore and some information about traffic on the streets in Singapore and some information about where a lot of taxis or cars are. Now, this is a physical space, clearly a very physical space. I would say it's a very conceptual space as well, and this comes to some of the conversation between Peter and Hans in the previous talk. I think a lot of what we think of as that are physical spaces, certainly Leibniz and Kant, I think particularly, would have described those as also, or even as primarily, conceptual spaces, that conceptual structures that we put upon the world as a means of organising our interactions with the world, organising what we know about the world, which starts with, not bumping into things. It includes how a child learns to pull themselves up onto when they're learning to walk, as we discussed earlier. And it certainly includes things like having an abstracted map of a place like Singapore, of having traffic information about it. It's very real, but the way we think about it is very, very abstract. Sometimes to figure out how far things are apart, I want to use a crow flies distance. Sometimes I want to try and figure it out in more detail. How long will it take to walk, or how long will it take to drive? So yes, in a sense there's one real world, perhaps, is a way to think about this problem, but there's certainly many conceptual structures we apply to that real world to help us navigate it for ourselves and other people. And one extra point on that is that I mentioned I have a passenger with a pickup, and sometimes they'll tell you a drop-off point in advance. That's a purpose. That it's not just an unmoving or space that is, say, or if it is moving, it's evolving under some prearranged dynamics. Ontologically, we could have the discussion about determinism, indeterminism. Is it really pre-arranged, or what would be a better word than arranged, but certainly for the practical purposes of the kind of work we need to do in the world, like if I could predict everyone's pick-up and drop-off point in advance, that would be problem solved. We can't. We have to work with the notion that the world is full of, in this case particularly people, we could say, well, living things, that have some purpose that you may not know in advance, and you have to understand that purpose in order to work together. And going back to the title, Semantic Spaces, Successes and Goals, is deliberately ambiguous. The goals part is ambiguous. I do want to talk about maybe some of the goals we could have for the next few years, but I think one of those goals is itself understanding and modelling goals, purposes. Second question on this side, why medical informatics? A lot of the examples I will go through of successes in the first half of this talk will be in the sphere of medical informatics particularly. That's largely because Trevor works on medical informatics. He was, before becoming doing a doctorate in New York and becoming a medical informatics specialist, he was actually a doctor in the South African Health Service. And so there's a big and very important application domain there, and for reasons I don't quite understand, or for reasons I actually don't understand, there's been a lot more recent interaction, at least that I'm aware of, between these semantic spaces, machine learning, artificial intelligence, and natural language processing than there has with medical and biomedical informatics. And maybe, well, anyone can speculate on whether that's true and why it is. I won't digress on that. So lots of examples from medical informatics, and we'll start with natural language driven examples, and then I'll talk about some of the things that we pioneered, or particularly Trevor pioneered really, on applying some of the models and technologies we'd developed with natural language applications to other sources of input data, particularly ontologies, groups of, in the sense of like groups of subject-verb-object or subject-predicate-object triples, and then some things about orthography, well that's natural language, so that counts, and tabular data, continuous varying quantities, things that NLP has not actually been very good at modelling yet, which are crucially important in medical informatics. So, and that's the introduction to the first half of the talk, which hopefully I will get through in time for the second half of the talk, which will be about purposes and goals. So, anyway, well-known semantic spaces. Why are we here? What are we talking about? We've talked a lot so far about vector space models, and that's particularly, I think, the main thrust of this meeting, which is great. We've had a ton of progress in this area in the past many years, actually. It's a good gradual story. We started in the 1960s with information retrieval and the vector space model for information retrieval. A 2-minute summary, you go through your document collection, you make a big matrix counting how many times each term occurs in each document, and I'll skip over tokenization, I'll skip over weighting, skip over any number of the things that actually make information retrieval very hard, and say we have a matrix, and as soon as you have a matrix you can add different rows in the matrix together, you can multiply rows in the matrix by a scalar, so you've got a vector space. Isn't that handy? Because you've got a load of linear algebra techniques that were invented back, well really crystallised in the 1840s to 1860s, and so it's very, very widely available. By the late 1980s, early 1990s, we have latent semantic analysis, which is, oh look at this term document matrix, it's very big and it's very sparse, and so information often gets spread out, lost, and it takes an enormous amount of space. The enormous amount of space we can deal with to some extent with sparse matrix technologies. The everything gets spread out and a lot of the information seems to get lost. That's still a conceptual problem, and so we started using singular value decomposition or other principal component analysis kind of matrix composition techniques to come up with a lower dimensional space. And so that's often been called a more semantic space. You see, this might be where the term semantic started cropping up in what had previously been a term document matrix. And this has progressed through several other numerical techniques, like non-negative factorizations to give a probabilistic interpretation. And most recently, there's been a lot of interest and apparently some extra major successes in using what's become called deep learning, which is really recursive neural networks that have been developed for a long time but have really come to maturity in the past few years, partly to do with the availability of enough computational horsepower to make them really scale. And there's been a lot of very exciting results in that space. You'll often come across the term embeddings as well, which is saying embedding words in a vector space. I found this term quite confusing to begin with, being a differential geometer by background. I always think of embedding as something that you put a curved object inside a flat space or something like that. So I thought embeddings was something new to do with differentiable manifolds, but it's used to mean putting words in a vector space. The important thing from that point of view, I think, message for this community is don't be put off by things like deep learning and embeddings. Oh, the ship has sailed on vector space models. They are vector space models, and a lot of the challenges we've been talking about so far, like composition, implication, ambiguity, resolution, and understanding how words really behave, are not now somehow made obsolete by deep learning and embeddings. They're more important than they ever were. So there's a really big opportunity for a community like this to take some of this work and say, hey, this is the ground space that we build our models on top of, and hopefully things get better and better. There's other spaces we could be talking about when we say semantic spaces. There's graphs, which we could talk about bipartite graphs, and we saw some Markov models earlier. And how do these kind of more discrete spaces interact with more continuous models? That's a very interesting set of questions as well. There's any number of good mathematical techniques, starting with taking the adjacency matrix of a graph, and just as with a term document matrix, as soon as you've got an adjacency matrix of a graph, you've got some vectors. And not just graphs in the nodes with links in between them, but we often have labelled links in between them, so we get semantic networks, the semantic networks, subject, verb, object triples. The World Wide Web is a kind of directed graph, at least it's modelled like that, and that's where some of the algorithms like PageRank came from and is used for a lot of the early successes in search of the World Wide Web. Then if you sort of combine the semantic networks and World Wide Web, you get the semantic web, as it's called, and there's been a lot of interesting use of data there, making it available. One of the sort of distinctions here, I think there's a very old distinction between atoms and void, or sometimes between discrete and continuous. These kinds of models are very discrete, very atomic concepts. These are in continuous spaces. One of the benefits of having a continuous space, a void that you can put new points into anywhere you like, is that's how information retrieval systems build document vectors, that you add up the term vectors and say, oh look, new point in the space, that's where this document lives. There's any number of other spaces that we could be using for semantic spaces, that like differentiable manifolds, orbifolds, simplicial complexes. We could have varying dimensions, we could have singularities. The richness of mathematical notions of space that is still to be explored, that could be really, really powerful for us, is tremendous. Okay, so I'm definitely going down that road of spending too long with introductions. So thank you. So let me talk about semantic vectors particularly. We know we can do superposition, weighting, and similarity detection. To mathematicians, we call these, vector sum, scalar product. Sorry, not scalar. Scalar multiplication, scalar product, and we can use these to compute, say, term-term similarities. Started with term-document similarities. Historically started for information retrieval. Term-term similarities for things like automatic thesaurus generation, and document-document similarities for things like relevance feedback. And the training to build a term-document model like this can be, the training to build a term-document matrix is just go through your corpus and count stuff. The training to build, say, a reduced model can be as simple as just pick some random vectors of some dimension, and one of the sometimes nice, sometimes nasty things about many dimensions is that if you just pick vectors at random, they will be almost orthogonal to each other, and then you can build relationships between vectors that you learn by multiplying those, what Trevor and I call elemental vectors, by your co-occurrence information. So you've got a collection of vectors over here, big term document matrix, you multiply these vectors by the term document matrix and you get a new set of vectors, and we call those semantic vectors. Obviously we could have, and many discussion stroke arguments do occur about, well, that's not semantics, that's just counting stuff. Well, yeah, could have a long digression on why in science and scholarship generally we end up picking certain names for certain things. If I called them vectors where we count stuff, I don't think this field would have got very far, so there we are. Now, this is all stuff that, when I've been saying we so far, I mean, we as a community. I was not myself doing the work in the 1960s, and very much benefited from the people who did. So from here on, I will be talking about stuff that particularly Trevor and myself did. So what next can we do with some of these semantic spaces? In the natural language area, we can predict future term-term co-occurrences. What do I mean by that? I mean an experiment where we took the Medline abstracts from about 1990 to 1996, and the task was try and figure out what terms that did not co-occur in medical literature in those years were about to start co-occurring in 1997, 1998. Why is this a good thing? It's a good thing because there is an enormous amount of medical literature. Part of the job of a specialist is to read that literature, hypothesize, oh, there might be a relationship whereby this drug that works for treating these different things might work to treat this thing as well. And then within the next couple of years, if that work is successful, a new abstract pops up in Medline saying that this particular drug treats this new thing that we didn't know it treated. So how could we predict that? If we could predict that, we could start building experimental hypotheses and actually proposing drug repurposing. We do a lot of experiments for drug repurposing. Drug repurposing is big business. I hope saying big business doesn't sort of make, oh dear, money, profit, a bad thing, in academic context. Why it's very important that it's a big business, if I said it was a very good use of the least action principle, that might go down a little bit better. The amount of investment and the time it takes to get a drug used in the real world to cure diseases is enormous. And a lot of that work is in the developing and demonstrating safety. So once you've got a drug out in regular use that we know has passed the first very important bar of not hurting people, if we can come up with, use informatics in any way to say that drug could cure more diseases, that's brilliant. That's a win for everyone. How we actually did this, if we just did the term document matrix and project down, we didn't predict the future very, very well, even using latent semantic analysis, singular value decomposition. So what we did is said, well, I started with these elemental term vectors, I multiplied by this matrix, I got these semantic document vectors, but I started with a co-occurrence matrix. All I need to do is transpose the co-occurrence matrix, flip it on its side, and then I can take the document vectors, multiply those by the transposed co-occurrence matrix, and get some new term vectors. So I have term vectors, train by multiplying by a matrix, document vectors, flip matrix over, train again, get back to some new term vectors. And you can do this process several times. Well, obviously you can do it as many times as you like. By the time we'd done it 3 times, that was when we got the best results for predicting what scientific discoveries the future was going to hold. By the time we'd done it 4 or 5 times, all the vectors were starting to look the same. You would expect that. In fact, you can use this process to, they all converge to the first eigenvalue. So we call this reflective random indexing, partly because the term and document representations are kind of bouncing off each other, and partly because we wanted to give the sense that the system didn't just read through the corpus and build a model. It read through the corpus and then reflected on what it had seen to come up with new hypotheses. Maybe that's a little bit fanciful, but anyway, it's done. Other things we can do, I'll call this ELD quantum logic because it started off a while ago. Using negation, using orthogonal projection for negation, actually it's a nice moment to say, this work did not start as a desire to apply quantum logic to semantic spaces. The person who sort of suggested this room is actually Oliver, sitting there. It started off as a bet, or not so much a bet at CSLI as a kind of you know, statistical semanticist and like formal logic training, having a discussion about what different systems can and can't do, and Oliver came up with a very good criticism of, well, you know, from a background in logic, it is pretty strange that you call something semantics and you don't even have a way of doing negation. And you know, we said, well, fair point, it's a very fair point. All we really do is add stuff up. Could we do negation by taking something away? Well, I guess so, let's give it a try. So, you know, we coded it up, gave it a try, and came up with this, you know, well, let's try and do orthogonal projection, because we were thinking of the situation where you've got, say, suit, which is got the lawsuit component and the clothing suit component, and if really clothing and law are orthogonal to each other, you probably only need to look at a courtroom to see that they aren't, but let's assume they are, then you project onto the subspace orthogonal to law over here, and you get clothing meanings, and that worked very well. So it started off as just oh, we can do disjunction, and we did some experiments about it, remove synonyms as well as just removing the single term that you said not for. So that's can be very useful when you're looking for information. And the link with quantum structures, quantum logic, that actually wasn't my idea either. I think that we were talking about this last night. That was feedback from, I think, Larry Moss in Indiana, who very kindly reviewed one of these papers that was called orthogonal negation for, and he sort of politely said, you do know that orthogonal negation is part of quantum logic. And that was a very, very kind bit of feedback. So that's what got us into looking at removing a disjunction as well. Well, we were already stumbling towards this. We had, if you want to say A, not B, or C, then you want something to be orthogonal to B and orthogonal to C, which translates into orthogonal to the plane spanned by B or C, and you get to the notion that something that you would flip using De Morgan's law in Boolean logic, you would flip using the idea that a disjunction is a plane in this vector logic. And then, one thing led to another. The logic of quantum mechanics was a paper written in the early 30s by Garrett Birkhoff and John von Neumann. Fascinating stuff. As Bob pointed out earlier, it did not really produce a revolution in the way quantum mechanics is done, but it certainly described a non-local, non-distributive logic that has some very interesting properties. By non-local, I mean, we had our suit vector here, it gets projected onto here. Projection, in a sense, is a non-local operation. We don't have the set here that we're restricting to some locality within the set. That notion of non-local in that sense, I'll make this generalisation. No, I'll make it later. Right. So good results in synonym removal. There's still a lot of work to do here. Nonetheless, there's still only so much you can do with addition and similarity. So what are some of the next things? A binding operator, a multiplication operator. We've talked about the tensor product already, which is in many ways the natural product operation for vectors. I'll confess now, Trevor and I haven't really used the tensor product very much in our work because of the coordinate explosion scaling problem. And because there are many alternatives. And one is the convolution products. The first one actually used by the people was the permutation, just permute the coordinates. Or you can take a convolution product, which is a tensor product. The simplest way of describing tensor product once you've chosen a coordinate basis is if I have, excuse the hand waving, but if I have a column vector and a row vector and multiply those together, is that the right way around? Yeah, if I multiply them that way around, I get the inner product, scalar product, a number. If I multiply them that way around, I get a square matrix. So that square matrix, the outer product, in a coordinate-free setting is called the tensor product. If we project down along the diagonals, as in just add up the numbers along the diagonals one way or another, we get back to a vector in the original space. That's called a convolution product. And it has some interesting properties. The convolution of two vectors is distinct from the vector you started with. It doesn't have a big cosine similarity with either of the vectors you started with. But if you're given one of the ingredients, and the product, you can recover the thing you started with. So it behaves a bit like a multiplication operator, and so we started generalizing or abusing notation. In the rest of this work, we use the cross-symbol tensor product symbol for any good vector multiplication operator that satisfies a lot of these properties that are called a vector symbolic architecture. This is kind of on its way to being an axiomatization of what we're talking about, but it still has words like dissimilar in it, as in, we would like some similarities, some scalar products to be large, others to be small. Axiomatic definitions don't really like words like large and small. So there's some work to do here, but in the process, there's some very interesting results. So, predication semantic analysis, definitely entirely Trevor's invention, is, I said we can take graphs and make vector models. Do you want to ask a question?
Yeah, just a very brief one for the previous slide. You have that release at the bottom. That makes it look a lot like a pairing operator. It looks very Cartesian.
Oh, you know what it is? This is a cut and paste from Windows to Mac. Got lost a symbol here. There's meant to, sorry. Thank you for spotting that. There's meant to be a circle with a divide slash through it there. Wow, you're paying attention to a list of many axioms. So, graph to vector model predication semantic analysis. We take a knowledge base of triples. So this is NLP in the sense of we took the output of an NLP system called Reverb that is maintained by the National Library of Medicine by Thomas Rindfleisch in Washington DC. And so we've got by now several million of triples, things like aspirin treats headache, though being not a native speaker of medicalese, they're of course much more complex. So fluoxetine treats minor depressive disorder, and that's one of the simple ones. And there's relationships like treats, inhibits, causes, and how we turn this into a semantic space in the sense of a vector space. We make these random elemental vectors for each concept and each relation, and then we make semantic vectors for each of them by going through the corpus, very much like we go through a term document collection, but instead of adding all the terms into a weighted sum that gives you the document vector, in the process we take this binding product with between the relation, the elemental vector for the relation and the elemental vector for the concept, and then we add it to the semantic vector. So now, by the time we've processed the knowledge base, each thing we're calling a semantic vector is a superposition of bound products of elemental vectors, not just a superposition of elemental vectors. But it's that close. And so, what did we use this for? We used this to recover or predict new relationships, the most important of which was an experiment where we predicted, or tried to predict, which pharmacological substances, where pharmacological substance is a generalization for drug, because all drugs are pharmacological substances, but lots of things are used in the laboratory that are not released as drugs yet, obviously. Used to predict which pharmacological substances would inhibit the growth of prostate cancer cells. And we got what I was told were very good results, in that about 30 out of the top 100 we predicted were found in the laboratory to inhibit the growth of prostate cancer. As an NLP background person, I thought 30% precision, isn't that lousy? But apparently, in this space, it's really, really good. And when we get what I would call a mistake in precision here, when you're going to all the effort to test things out in a laboratory, apparently that takes a long time and costs a lot of money as well. So in terms of the cost saving here, we're talking about a lot more than, oh, I didn't like this document, I better click the back button. So that's a really nice example of using a semantic space technology for a kind of reasoning and inference, like taking premises building some kind of conceptual model for them, drawing conclusions that has been of, to say it's been of practical real world value, there's still a long process for these things that were predicted and found to be usefully inhibiting the growth of cancer cells to actually prevent the growth of cancer cells in people. There's a long way to go there. It's a big, complex machine. But it's really interesting stuff there. And one of the things you might note is traditionally, or maybe not traditionally, but in the sense of the past 20 years, I've often encountered conversations where there's a kind of territorial truce between empirical and symbolic approaches to language processing, which is like, you extract, like empirical methods are all right for extracting stuff, you know, maybe extracting some stuff from corpora. Once we want to like reason about it and deduce new results, we better move to more symbolic methods. This was the other way around. The reverb system that extracted the predicates in the first place was largely a symbolic pattern matching, handcrafted, good old-fashioned handcrafted information extraction system. And the thing we're using to reason about from those premises and deduce new results is the semantic space model, the distributional model.
20 minutes.
Okay, thank you. Now, once we had all these products, we started superposing them, because saying aspirin treats what, I might get other things that aspirin treats, good, but I kind of knew that already. If I say aspirin treats plus any number of other drugs, think of a long list of drugs, bind them with the treats relationship, I can start to use this for analogical reasoning, sort of A is to B as C is to what. So this led to a paper called what's the fluoxetine of Prozac? Oh, sorry, what's the Prozac of schizophrenia? And so using all of these, like literally all of the drug treat disease relationships to build a single vector that somehow encodes the notion that some stuff treats other stuff, and then I mentioned the binding and release operator. Then you take the drug whose new treatments you want to find, you use the release operator on its vector with this thing you build up as a big superposition of products, and it starts to churn out things that it turned out in evaluation that drug would plausibly treat. So that's how it was used for drug repurposing. That's the practical side. Some of the more conceptual side that this audience might be particularly interested in is we've got some quantum-y things going on here, or things that we normally talk about in a quantum context. We've got superposition already, we're adding things up, but we're also adding up products. And we add up lots of pairwise products and get a combined representation from this sum of products that you could not get by just decomposing it into two elements and saying it is the product of these two elements. Mathematically, that's how we represent entanglement. And now I will pop out and make the generalization that one of the interesting things I find about this work is a lot of the quantum things like non-local projection, that's kind of spooky, and you know, in quantum mechanics that sets up this kind of dichotomy between quantum mechanics and special relativity, and we get into some serious difficulty there. From a mathematical point of view, all we're doing is projection. What's the difficulty? Entanglement. Mathematically, let's go back to the tensor product. If I take the product of two vectors, how many degrees of freedom do I have? I'm going to rush on, so I'm going to say 2n. Right, we know the answer is 2n. If I build a square matrix, how many degrees of freedom do I have? n squared. So for n greater than 2, there is no way I should expect to be able to produce n squared coordinates from 2n degrees of freedom. So there's nothing strange about entanglement in the sense of you can't get every product from just pairs of elements. We only get to strangeness when we talk about the physical interpretation of, well, it's two particles that might be a long way from each other, and this is getting spooky. So, a few extras on stuff we've done. Orthographic encoding, bind a letter vector with a position vector, generate a position vector for how far along the word you are. Thing with those position vectors is we can generate them by linear interpolation, not generating them randomly. So we deliberately start with some vectors that are not orthogonal to each other, but have a kind of graded relationship in between. And that led to some nice results on building up representations for orthography, and you can measure the difference between words on a sort of, in the sense of words as a string of characters. So, like Levenstein distance is one of the traditional ways of doing it. This is an alternative. Computationally happens to be linear rather than like quadratic. Other benefits. That led to work on gradable quantities in general. One of the bad things we do way too often in natural language processing is, you know how a lot of the things we're a little bit embarrassed about get slipped into little sentences here and there. And one of the things we're definitely embarrassed about is the process was the corpus was pre-processed to remove stop words and to replace numerical quantities with a symbol for numeric quantity. Great. It works for what it does. It obviously loses information. There is a semantic difference between 27 and 2700. And not surprisingly, when you're doing medical informatics, it's a very, very important distinction. Because if you're trying to tell whether someone has high blood pressure or not, you better be able to tell the difference between 180 and 140. So, same idea used for modelling gradable quantities in a gradable fashion as semantic vectors. This is one of those astonishing gaps. It is astonishing that we've been using these continuous models for years, for decades, and one of the main things we have not been using them to represent is physically continuous quantities. So, what other predicates are out there? You can come up with a kind of type system for that. We've recently used the same orthographic encoding for gene sequence similarity, and so we can represent a lot more than documents and queries. So that's it started with NLP. We're using it for the same ideas for a lot more domains by now, and it's really interesting. Okay. Questions that have come up several times, so I'll answer them now quickly, but how long do I have left?
You've got coming up to 10 minutes.
All right,
so
thank
about
you.
12.
All right, 2 minutes on this slide then. The question that's been asked several times, you talk about quantum logic or entanglement or superposition. What's really quantum about it? Is there any like real quantum mechanics going on here? My opinion by now, you might think this is strange having been working in quantum semantics. If you wanted to get into the newspapers, you'd call it quantum semantics, of course. But everything I've described is a mathematical technique that happens to have been used in quantum mechanics starting around the 1920s, 1930s. But they're all mathematical techniques that were invented long before that, particularly the work of Hamilton and, most importantly for varying dimensions, Grassmann in the 1860s. So I can't possibly make a case that a quantum mechanical interpretation is necessary for something that was invented before quantum mechanics. So that's a historical answer to a very... But I think the historical answer avoids... it gives you a quick Boolean answer, whereas a philosophical answer might turn into more of a debate. But what I will say is, just because it's not quantum doesn't mean it's classical. Let's talk about some things that we say, and when you read one of these news articles that talks about the latest advance in quantum computing, you'll often find another of those what I consider dirty laundry sentences. It's not like quantum physics, i.e. the physics of everyday life. What do you mean everyday life? We live our daily lives in a world where let's keep this to the simplest form. The past can be remembered but not changed. The future cannot be remembered and can be changed. So we're dealing with lots of problems for which classical physics does not help us. Like, for example, where is my next passenger going to show up? But now, in the last 5 minutes, I'll do the second half of the talk. So we've done a ton of stuff. What could we do? I would really like to see us doing a better job of modelling purpose and goals, rather than, but because we haven't done this very well in physics particularly, since classical mechanics was so successful. There's no real purpose and goals in classical mechanics, so thank you. Every time we need purpose and goals, they kind of drop into our model, kind of deus ex machina, and we really should try and do a better job of making purpose or goals part of our models. And I'll get on to why in a minute, or why we as people should do it in a minute. Part of it is it helps us to understand the natural world very easily. So the example I like to start with is a dog. I have 2 dogs. I think I love them dearly. I love them dearly most of the time. They're very, very simple creatures. They're, especially the younger dog, who's a puppy, wants to chew lots of things, but the older dog's getting much simpler to understand. His life strategy is basically look cute, get fed. And he does it all the time. He will sit there all day inside sleeping or looking cute to try and get fed. Now, generations and generations ago, looking cute would not have done him much good for getting fed. Running fast was much more important for getting fed. And we can model this as a kind of semantic space. Here's get food. That's what he wants to do. So let's call this an objective axis. Objective axis. Well, what are his strategies for getting fed? If he's a wild dog, run fast. So the wild dog has a kind of point of view that says, if I think of the world from over here, the run fast axis and the get food axis are very aligned. So that's the way I'll think about the world. The tame dog, the domesticated dog, says, well, this looking cute thing seems to be doing very well, so I'll align my view of the world so that looking cute and get fed are aligned, and I'll scope my behaviour, I'll learn to behave in that fashion. Now, I'm not saying that there are these axes inside a dog's brain any more than I'd say that singular value decomposition is going on inside my own brain. But it's a way of thinking about the situation. And it's a way of thinking about the situation that might help us out of some things that are somewhat intractable conflicts at the moment. So let's take global warming. This is a way of... so we have people who are called hierarchical individualists. This is mainly work done by Kirsty Kitso, a collaborator in Australia. And so there's some cognitive science background that I will skip over here. But there's a way of modelling points of view that says some people are more hierarchical, some are more egalitarian, some are more individualistic, some are more communitarian. And generally people who are fairly communitarian and egalitarian tend to believe in climate change. People who are very hierarchical and individualist tend to not believe in climate change as much as anything because they know they're different from these people. That's getting us into a discussion about climate change that just isn't helping us recognise and solve the problem. And so this is a point of view perspective. This is very much the way a paper like The Economist will write about climate change. It's stop telling the hierarchical individualist people that they must believe in climate change. It's not going to happen. Too much identity tied up with it. Do say things like, we need to manage resources very well, because if not, commerce is going to become less profitable. There are people who are, say, somewhat individualist but quite communitarian, who think the personal health approach, like, I might not believe in climate change, but I do think planting trees in a neighbourhood park is a good thing to do. Great, so let's plant some trees in a neighbourhood park. We can argue about climate change while we're doing it, or we could not argue about climate change, but let's still plant the trees. So the way this you see what we've done with the dimensions is, instead of sticking to a model in this flat plane where people are at loggerheads, add an objective axis that even belief in climate change isn't a goal in itself. A sustainable, prosperous world is a goal in itself. So let's work out, everyone can agree a sustainable, prosperous world is a good idea, and then let's work out different actions that people with different beliefs are likely to be motivated to take because of that. So, like I said, there's nothing dramatically new here. This is the way some newspapers have been writing for a long time. It's just a way of understanding it. Similarly, current US elections, what's going on? I suspect the rest of the audience is less sick and tired of this topic than I am. So let's talk about it very briefly. We have this supposedly standard political axis that is, you know, conservative to liberal, or you could call it left to right, or there's a lot of sort of strange abusive terminology here. In the Victorian era, you know, liberal would have been more over here, and this would have been like dangerous socialist anarchist revolutionary or something like that. But now we call these conservative and liberal in the States. And along this axis, you know, you've got Hillary Clinton, Bernie Sanders on one side to different degrees, and some Republican candidates on the other. What we're seeing is that that traditional axis isn't explaining very much of people's motivation for who they sympathise with and who they vote for. There seems to be a big belief that we need change. Whatever it is, it needs to be different from what we've done before. So there's a traditional to radical axis, and the people who are more radical in their desires are tending to prefer the Donald Trump or Bernie Sanders approach. There's another thing this diagram hides that would be in the semantic spaces, and is an interesting topic on what's happening. Traditional might be an axis, radical, thinking of radical as not traditional. Let's go back to the orthogonal projection we were talking about. What we should really have is radical as an orthogonal subspace to traditional. And then we'd be able to point out that traditional might be one axis, but radical, like, I just want things to be different. If you're in a 100-dimensional space, there's 99 dimensions of how to be different. In that sense, radicalism is not a policy. It's just not wanting something. So I think that goes some way to explaining why what these people have in common is actually not necessarily very coherent. I suppose I've slipped into a little bit of personal opinion here. I think the anti-traditionalist point of view is just really not very coherent, but explaining that in terms of, well, if you've got a traditional axis, then the normal hyperplane to that's going to be just n-1 dimensions. That's very, very many things. Don't consider it. Good luck me making that point as a political argument. But this has led to lots of contradictory beliefs and statements about what things are good and what things are bad. If the general statement, voting should be weighted towards more politically savvy or active or passionate people, that's a direct contradiction of the one person, one vote principle. There are times when we might say this is a good thing, might say this is a bad thing. What we've seen is lots of sort of, well, caucuses are a good thing, open primaries are a good thing, closed primaries are a bad thing, superdelegates are a bad thing. Well, hang on. Closed primaries, superdelegates and caucuses are all ways of preferring people who are more deliberate, more active, more passionate about their politics. So what's really the generalisation here? It doesn't fall into a coherent axis. It doesn't fall into a coherent symbolic logic statement. It doesn't generalise. What it does is appeal to similarity with something that people feel. And a lot of reasoning seems to happen this way. So one of the things I nearly finished. I think I have really, really nearly finished. One of the things oh dear, oops, I shouldn't touch my keyboard. we go. So this is just one example, and I apologise if I happen to have picked an example that is, dear to anyone's heart, and so I'll buy you a pint later and you can call me horrid. But there are so many situations where people are not logical, and by logical I mean logical in the strict Aristotelian, let's look at the structure of the sentence. If changing the variables, changing the nouns in a sentence can change your evaluation of whether it's true or false, then your deduction is not following logic. It might be following other principles, but it's not logic. And so how do we explain a lot of those situations where we change some words and change someone's conclusion? Well, a lot of the time what seems to be going on is there is an affinity with different words and different positions, different senses of self, different senses of identity, and the notion that, human reasoning is really logical, and these continuous distributional empirical spaces are a kind of poor approximation to that. I think that's only the story in certain pretty constrained situations. I think there are a lot of situations where actually the continuous, well, this thing's kind of close to that. That's why I feel I have an affinity with it. That's why I'm likely to accept this statement, is what we see happening a lot of the time. So, I'm supposed to have finished, so I will finish. This is one last slide, I promise. Practical suggestion, some parts of which I think would not be very hard. At a high level, I'd like us to try modelling an author's goal or motivation as one of these objective axes. What is the author trying to do? Some of the generative approaches to so-called probabilistic generative approaches to explain language generation do not, in my opinion, explain language generation. They say, oh, you pick a topic and then you draw things probabilistically from that and you generate a document provided you stick to grammatical rules. Well, all right, how do you pick a topic in the first place? What topic is being picked? Why is it being chosen? The joke earlier, well, so-and-so wanted to get a publication because they need to get a job. Well, we know it's a joke, but we also know it's a joke because it's true, not because it's false. And if we understood that on the high level, understand on the low level what connotations words carry. Words do carry connotations. Smell, odour, fragrance, stink, aroma might all have similar meanings. I cannot swap them in a sentence and come up with a sentence that means the same thing, at least not to a reader. So if we try and align some of these axes, the purpose axes and the connotation axes, we could understand better what an author's motivations really are. Sometimes maybe uncover some of the slightly more sneaky hidden motivations. We could maybe even try and automate the process of doing this somewhat better. Don't choose this word, that'll annoy these people. You didn't really realise because you didn't really talk to these people very much, but don't pick that word. Pick this word instead. And we might come up with better ways of automating the process of persuasion. Is that a good idea or a bad idea? I'll leave that for questions.
So we've got time for a couple of quick questions. Fabrizio?
In the slide about wild dog and the dog, the way I see it is like there is a couple of strategies that the dog can adopt. So have you thought about how can you implement a strategy change in this scheme? Like, let's say the wild dog gets adopted by a... Yeah, what happens then?
Right. Yes, and it's quite interesting. Assume that the dog has finite resources with which it can consider different options.
Okay.
Not necessarily take actions yet, just consider different options. Then in this run fast, tame, the run fast, look cute space, if the dog adopts a position of what it's going to pay attention to, which is somewhere along that, let's say it's a segment of a unit circle, because we're normalising our vectors, by the nature of the way cosines work in differentiation, If I move 10 degrees in this fashion, I gain a lot of ability to pay attention to this axis and lose very little paying attention to this axis. So if you took a kind of probabilistic or Manhattan normalization, it would be somewhat hard to explain why, well, any dog that even thinks about trying to look cute is going to lose food in the meantime. If you model it as a circle, then the dog who keeps looking around a little bit is actually losing very little and might get rewarded quite a bit to begin with. So a version where you normalize based on Euclidean distance rather than Manhattan distance might be a better model for explaining why something might be encouraged to consider several options. It's also another good case of, oh, you said Euclidean norm, that's quantum probability rather than regular classical probability. And to me that's another of those, well, yeah, just because I squared things before I added them up, I'm not going to say that's quantum, that's squaring.
But why this resistance if you use mathematics introduced by quantum theory? Surely you're doing quantum stuff.
Surely? Like, I mean, so to begin with, my original, a lot of the mathematics we talk about was not introduced to do quantum theory, so certainly all of the things, say, pre-1930s, that argument wouldn't really apply to, but then for things invented since then, mathematics has such a long history of something that was invented with one problem in mind being used for another problem. Like, because you use a differential equation, it doesn't mean you're studying heat transport or wave dynamics. You could be studying something quite different.
Okay, there's one question here. There's Alex.
Yes. This one here. Yes, I think your definition of difference as choice between options reveals how difficult it is to map the human and in your example politics, because we don't have only to map what is there, but also what can be created, right? And some people would argue that difference is about creation and not just choosing what is there. I'm referring to your opposition between radical and conservative. Mm-hmm. So, how do you map? I mean, I think one interesting question is how do you map the probability of the possibility of creating something that's not in the landscape?
Mm-hmm. Right. Since I haven't, this is going to be a very off-the-cuff answer. I look at history. How did the idea of, to take the American Revolution, how did the idea of we need change, we're going to not have a king? What do you mean we're going to not have a king? You can't get by without kings. We could give it a try. And new ideas sometimes come about. Now, particularly that idea came about because, originally they were really annoyed with Parliament and only gradually became annoyed with the Crown as well. But there was a desire for change, there was a stimulus for change that could kind of attract that desire once it was seen how many of the actually quite oppressive policies that were not so much revolutionary in the sense of demanding new freedom, but were reactions against introducing policies that were restricting established freedoms. There was clearly a grievance there, and there was something it could coalesce around. And so I would say maybe once you have the something it can coalesce around as well, that's when out of the large subspace of potentially changing phenomenon, something might get selected, a bit like the speck of dust around which the raindrop forms.
Alex, did you have a question?
Yeah, probably struggled a little bit even to formulate this question. It may be a very naive question. On one of your earlier slides, you were mentioning the possibility of using representation spaces that are richer in structure. than simply a vector space has not very much been explored. It did occur to me that, this is the part where maybe I'm very naive, that if you're in the business of embedding a large corpus of words, relations, facts, whatever it may be, as vectors in a vector space, and if the number of these things really is quite large, there might well be constraints, maybe constraints you didn't even realize were there until you actually plot this thing. You might find that you've got, for instance, something that looks like a reasonable approximation of some sort of surface sitting in vector space, but non-linearly. And then if you wanted to track how things are evolving, and all of a sudden you're trying to model the evolution of a surface. If that were to be the direction in which some of this work were to evolve, would that then present you with a level of computational complexity that would render the whole project somehow very problematic? In other words, if you had to do all that you've been discussing but subject to some nonlinear constraints,
yeah,
possibly evolving, what would you do?
Right, what would I do? I think to sort of pass on the question, I think one of the first things I would do is talk to Peter. The notion of, like, we're not just, once we have flat spaces, we're tempted to think of subspaces, lines that extend to infinity, good old Euclidean axioms, some of which just don't apply. There is no, I don't believe that because we're using a vector space there should be a straight line that is parallel to the straight line between bottle and shirt that passes through Glasgow. It just doesn't make sense. So we could talk about things like convex regions. Because I have red and yellow, I might be able to put orange in between it once I understand red and yellow, but it doesn't necessarily mean I can understand blue. We should be more focused on interpolation than extrapolation, and the reason I mention Peter is because I encountered that idea first, in particularly the discussion of colours and colour descriptions in the colour spindle in your book. But sorry, that's conceptual motivation. Mathematically, yes, it would get harder, definitely. Yeah, quantizing a differentiable manifold is hard and intractable, and that's that's, as I understand it, the principal reason why a general relativistic combination with quantum mechanics is so mathematically difficult, because we don't have very good ways of quantizing a differentiable manifold in the same way that we can do like eigenvalue spectral decompositions in a flat space.
Okay, thank you. I think we'll keep any other questions to the break, and thank Dominic again.